I will be talking about, again, the minimal and maximal surface. So let us start from a few things which we have discussed in the last class. So C started from a map. Let us X a map U to R3, and then C said when it is a minimal surface. So then the point was, and then yesterday you have seen, X, you just write X is X1, X2, X3, and then you have seen in an isothermal parameter. Isothermal parameter S comma T, if I say, in isothermal parameter, and if you calculate, if you write on these maps, phi k is, if you write on these map, see, in isothermal parameter, if you write on these maps, then I will. So these phi k's, okay, I will just write it again because these expressions are important. Yes. Okay. So I defined phi k is 1 by 2 del by del x k over del s. Now it is visible. Okay. So these phi, if I define these phi k, so we have seen in isothermal parameter, again I'm writing here, isothermal parameter means, in isothermal parameter means what? What we are expecting, del x k, del x over del s, this norm of this is equal to del x over del t, and del x over, this is 0. This is isothermal parameter. When I say isothermal parameter, so S and T are isothermal parameter. So in isothermal parameter, we have, if you calculate phi k square, so in isothermal parameter, phi k square turns out to be 0. And this we have seen in the last class. We can again derive in the today evening if you want, or you can see the Osserman. I will give the reference. So these, yes, phi 1, yeah. So this is greater than 0. So this if you remember in the last class, this turns out to be G11 plus G22 in isothermal parameter. This expression. So if X is a minimal surface, which we are taking as a regular surface. So this condition, if I say mod phi 1 square plus mod phi 2 square plus mod phi 3 square is greater than 0, this means greater than 0. This means this means this is a regularity condition in an isothermal parameter. So you start from a map X, write down phi 1, phi 2, not just for a minimal, not just for minimal. You start from map X, write down phi 1, phi 2, phi 3, and calculate this thing. And this is in isothermal parameter. This is greater than 0. This means if and only if surface is X map. Surface means this map X is a regular. In the minimal surface, what is the minimal surface? Minimal surface are the surface whose curvatures, last class you have seen, mean curvature vanishes. This means the principal curvature has are equal and the opposite, k1 equal to minus k2. And that condition is equivalent to say that each xk's are harmonic. If I identify, and this is in isothermal parameter. Again, we have to, in isothermal parameter, this is ST isothermal, and this condition is equivalent to say that mean curvature vanishes every point. I will use the symbol. So go through with this. So we start from phi 1, phi 2. We start from map X in an isothermal parameter. Whether there exists isothermal parameter for minimal surface. Minimal surface you can define without starting isothermal parameter. Whether there exists isothermal parameter for a minimal surface or not, that is, let's leave those questions for time being. Suppose there is a, suppose the starting point is also an isothermal parameter. And then this condition is basically equivalent to isothermal parameter. And in isothermal parameter, this condition is basically says that the surface is regular, and this condition is the surface is minimal. So this, and I'm going to write it. And then this, and what is, if xk's are harmonic, if you identify this as, so then xk's are harmonic is equivalent to say that is phi k's are analytic. In this, is phi k's are analytic function, y Cauchy Riemann. If and only. So minimal surface, now the minimal surface geometric meaning we have in the, we have seen geometric meaning is basically every point is a saddle points. K1 and K2s are equal and opposite. So this is, and then to work with this type of this type of surface, we have this, we can use this as a definition basically. Minimal surface are x such that, so let me define the minimal surface definition. So minimal surface are x from U to R3 is a map. I will start from a map, just a map. May not be, see map, a smooth map, let us take. And then, if this is equal to 0, smooth map and parameters, so this is the definition of the minimal surface. This is the definition of the minimal surface. Okay? And in the last class, you have also seen. You start from this is a way. So you have seen in the last class. You start from any analytic function phi 1, phi 2, phi 3. You start from any analytic function phi 1, phi 2, phi 3, such that this is 0 and this is greater than 0. You start from any analytic function phi 1, phi 2, phi 3, such that this satisfies. This will give you last class you have seen. This will give you a minimal surface given by. And xk is real part of, there is no need to write 2. If you want to write 2 to just make, so to at least it will match. So 2 real part of any analytic function is simply connected domain. You start from any analytic function in simply connected domain. Then this will define. Then this will define. You can see, you can calculate in the tutorial, you just solve basically, you solve what is del xk. So this is a minimal surface basically. This condition will ensure parameter is isothermal because for these xk, if you calculate del xk or del s minus del xk over del t, so you will see that is equal to phi k. And these xk, for those phi k, we have these two conditions. So from there, it is a minimal surface. So minimal surface, and this is basically regularity condition. Sorry, isothermality, and this is regularity condition. Regularity means what? Regularity means del x over del t and del y over del t are linearly independent. This means you can define the tangent at every point. Basically, you are asking this thing regularity. Okay. You may basically relax this condition. You may relax this condition. To just say, okay, you are to just because there are texts you will see this this definition, generalized maximal surface. People say a generalized minimal surface. So people are generalized minimal surface means what? X case for those phi case conditions is basically not equivalent, not identically equal to 0. This is not identically equal to 0. Maybe 0 at some point. So those are generalized minimal surface. So see here simply connected. What is the importance of this thing basically? I started from a map from a simply connected domain. Because of this integral makes sense. What do you mean by Z0 to Z phi k dz? This means you are integrating along any path. You are assuming that this integral is path independent. Phi k's are analytic functions. I said phi k's are analytic functions. So you can start from those phi k's. So see, to get the minimal surface, so this is the one thing. You start from a simply connected domain and choose phi 1, phi 2, phi k such that those are analytic. Starting point is simply connected. And analytic such that these two conditions satisfied. Summation phi, you may, but remember all those things in your mind. See, you are taking simply connected because integral makes sense. You are taking the first, you are asking for the first condition because of the isothermality. You are asking for the second condition because of the regularity. Remember these things in your mind. And then now if you want to relax the condition, suppose if I start from a map X from some open subset of C2R3. So what condition I should and those phi k satisfy this, those phi k satisfies this. But see, I did not start from a simply connected, so this integral may not make sense. So put one condition, suppose this integral makes sense. People use here real period vanishes basically. Those phi k's, if you start from a real period vanishes. So basically, idea is you start from phi 1, phi 2, phi 3 such that this makes sense and this holds. You have a minimal surface. We have forwarded article. In those articles, you may see that this condition people are relaxed in some sense, some cases, because people are interested in behavior of surfaces where this basically goes to this is zero. This is called some singular set or something. We'll see. Okay. You have a lot of examples, phi 1, phi 2, phi 3. From here, you have a Verstappen representation, which you have seen basically in terms of FNG. So in this 3 lectures, we will be discussing this is what we discussed the minimal surface. So we will discuss minimal surface and maximal surface. Let me again, so these are the basically method to get examples and other things. So minimal surface are the surfaces you can basically read are geometrically. One thing you know, every point is saddle point. Second point is if you take any point P in that surface, so that is a local area minimizing surfaces. Local area minimizing, not the global. Remember this point. Locally area minimizing. Area you can talk about in a metric. Area you can talk about in a metric. So if you change the metric, can you, in the surface is same. Surface is same in the sense that mean curvature vanishes condition are there. So there are space called the Lorentz-Minkowski space. We'll see. So in those spaces, the similar type of surfaces which are locally area maximizing, similar type means the mean curvature 0, are called the maximal surfaces. We'll come to the precise definition of all those things. So minimal surfaces and maximal surfaces, and we'll see. So these are we'll see what happens. But before going into detail of the maximal surface, as we know R3 we have feeling. Okay, what is R3? What are the independent vectors and other things in R3? We can discuss. So yeah. Okay, so this is, of course, we don't know a lot of things. So maximal surface is 3-dimensional Lorentz-Minkowski space. Is a space like immersion. What is that? We'll try to learn everything which is so Lorentz-Minkowski space. What is that? Space like immersion. I will give you some feeling of mean curvature vanishes. So mean curvature vanishes everywhere. This we know at least. But is there any? We know in a sense if we can define a similar way. Is there any other way to define the mean curve? Is there any different way? So we'll see, is there whether it is different in Lorentz-Minkowski space to define the mean curvature or that same? So we'll see. First of all, let us explain, let us learn all these words, all this Lorentz-Minkowski space first of all. And then we'll go to, so this is the notation we'll be used, E13. E13 is a Lorentz-Minkowski space. So what is that? It is a vector space R3 with a different matrix. So it's a vector space, don't worry. It is just the same. Lorentz-Minkowski space is a vector space R3, but the last, you define a bilinear form. Metric will say this. This will say metric. So last, if u equal to u1, u2, u3, and v equal to v1, v2, v3. So last is basic minus. So this is a metric. With this metric, we want to basically understand what are the similar type of surfaces in this space. So this is, but as soon as you put this metric, so you don't have that conditions which you had in the Euclidean space. What is that condition? VV, inner product of VV equal to 0 if and only V equal to 0. Here you may have some vectors which are not equal to 0, but vector is not equal to 0, but length, some kind of length, basically inner product of VV equal to 0. So suppose V equal to x comma y comma z. So what are those vectors? Those vectors are x comma y comma z such that x square plus y square equal to z square. These are the vectors. No? So all those in double cone basically. These vectors are the vector. These are the vectors lies on this cone are of length 0. Length 0 in a sense ki VV equal to 0. But V is not equal to 0. Okay, so just a minute. Yeah. So this vector is 0 vector is also satisfy this condition. 0, 0 is 0 basically. So all those vectors. So vector. So we have basically three type of vectors here. V is said to be space-like if VV is greater than 0. And 0 vector by default we will be assuming this is a space-like vector. So 0 vector is a space-like vector. By convention, we will be using this thing. And the time-like, if less than 0, VV, and the light-like, if it is equal to 0, but V is not equal to 0. So 0 vector is not a light-like vector. These So these are not random terminology, space-like, time-like, light-like. It is coming somewhere. So I think, so you just explore. So yeah, it is light travels along that cone and then, so there is a physical meaning associated to these words. This is not just random things. It's just not we are putting this. So this is the space-like region. The vectors here are all the space-like. Vectors here are all the space-like. Vectors inside that cone are time-like. Cone is not stops here, and then the vectors on top of cone are the light-like. Similarly, you can define space-like plane, light-like plane, time-like plane. Space-like plane are the plane where the metric is positive definite. You know metric is so you have this metric now. Metric is positive definite. Metric index of a metric, and then when the metric is degenerate, so basically the easy way to just fix some basis of E13. Basis you can talk about. No, E13 is just a vector space R3. You first fix a basis of E13, and you can write down the matrix. Just see matrix will be symmetric, so the eigenvalues are real. Okay, just see how many plus and how many minus eigenvalues are there. So minus are the number of the negative eigenvalues. These are this is the index basically. If the determinant of that matrix is greater than 0, matrix is greater than 0, matrix is said to be greater than or equal to 0. I will say here, positive definite. So 0. Can you give me one subspace of R3? 0, na? 0 subspace. So whether it is a space-like or time-like or light-like. E13 is a space-like, time-like, or light-like. This is also subspace. So E13 is a time-like. How? Why? You just calculate you just fix a basis, some basis of R, even 3. Some basis of even 3 means basis of R3. Write down the matrix representation of this matrix. And then you will say one entry is -1, another eigenvalue 1 is minus. In the standard basis, eigenvalues are 1, 1, and -1. So basically, precise definition is this. UB is subspace of R3 if the induced matrix, Minkowski matrix, that matrix is said to be, we will call Minkowski matrix or Lorentzian matrix sometime. So if that matrix is positive definite, we'll say it is a spacelike. If index 1, it is a timelike, and matrix degenerate, it is a lightlike. Okay. 0, 0, 1. 0, 0, 1. This is a vector. This vector is lightlike, timelike, or spacelike? Tell me quickly. 0, 0, 1. 0, 0, 1 is timelike. Okay? What is and then this vector spans a subspace. Take the subspace spanned by this vector. So what is that subspace? Whether timelike, lightlike, it is timelike. You take a lightlike vector, you may get lightlike. You get two lightlike vector independent. Two independent lightlike vector. One is here, one is here. You can take, na. And take the subspace spanned by these two lightlike vector. This is 2-dimensional subspace. This may not be timelike, and this may not be lightlike. So obviously this may not happen. You have to verify basically. Verification is write down the matrix representation of that matrix representation of that matrix in some basis basically, and then see what is the index. So it is a result It is a result. If you have two independent timelike vectors, then the span. Sorry. If you have two independent lightlike vectors, then the spans will be timelike subspace. There are references for all those things, so it is better to just write down the reference before talking all these things. You can read all these details. This is reference I'm writing here. Reference is Rafael Lopez. So differential geometry of curves and surface in Lorentz-Minkowski space. Title is differential geometry of curves and surface. In Lorentz-Minkowski space. Okay, so this is the reference. You can find, this is not a text. He has uploaded an article in archive. So you just search Google. So it is a very famous article, and the people are all following his article, and the archive article. This is not a textbook, okay? Archive article, and you can find over Google. And this is for the maximal surface. So maximal surface, the things which I will be covering in the next 3 classes, basically most of the things from here. In the one of the article which we have forwarded, interpolation, article title is interpolation. So most of the things will be from here in that article basically. And for the maximal surface, for the maximal surface or for the Lorentz-Minkowski space. For the minimal surface, there is famous text is basically Ulrich decrease. Dear case, okay. And then is Stephen H. These are the title, author name. One text basically is by 3 authors. Text name is minimal surface. So minimal surface, chapter 3 basically. No, timelike means inside. Sorry, so okay, yes. If you have confusion basically, so this means basically inside that. It is not on the top. That's what I said basically. On the top, on the surface, everything is lightlike. It's just okay. So these are the reference basically. Chapter 1 is chapter 3 basically. We will be dealing here, and then okay. lot of things you can see. You can see from here. See, if you take two independent vectors, one more fact I will just share with you. Two independent light-like vector. Two dependent light-like. Okay, let us start from dependent. Two dependent light-like vector. So what will be their inner product? Inner product means what will be, if V and W are two dependent, what will be the matrix, what will be the V comma W? What will that? Light-like, these are light-like, two dependent light-like vector. What will be the V comma W? 0, na? That is 0. This is if and only if condition. If you take V comma W light-like, V, W equal to 0, if and only if V and W are dependent. Tutorial, we can see this thing in the tutorial. If and only, this is if and only if. So it is not just, it's not the same as a R3. In R3, is this clear? No? So there are at least, I'll strongly recommend at least second page. There are a lot of results which you at least make you understand about the Lorentz-Minkowski space. Okay, so let's, if you have a form, this is standard technique basically. Construct a map from V to V star and then rank nullity theorem basically. The first result, dimension of U perp. What is a U perp? Definition? The same definition, but in this matrix. U perp is all those vector V in even 3, such that VU is 0 for all U in U. Are you following? Okay, so this is U perp, and the V is space like, then RV perp is time like. So again, how to prove V is space like? You start from a space like, V is space like, and then extend the basis to even 3, and then see the remaining basis, calculate the matrix in that basis basically, of the perp basis. You will see that matrix is index 1, like routine process. So, but at least do all those things, and if you are not able to do this, we won't be able to cover in the tutorial, but you can discuss with me. I am available here. You can discuss, otherwise, so yeah. So timelike, light-like subspace, you can ask a question whether this subspace is spanned by this is a random question, whether it is timelike or light-like or not, to get just equipped with all these. Anyway, so we understand what is the space-like, timelike, and light-like subspaces. Now, let us go to the curve. Our aim is basically to understand the surface in this space. Let us start from the curve. So curve is same definition, smooth curve. Curve I mean smooth curve. Okay? Smooth. Alpha is a map from some open interval R to even 3. Alpha 1 t, alpha 2 t, alpha 3 t. Same the differentiation. Alpha 1 prime t, alpha. So this is the curve, smooth curve. So we can ask whether curve is space-like, time-like, or light-like. So curve may not be any of the above type basic. So we will say it is a space-like if. Space-like at t. This is space-like at t point. If alpha prime t is behavior of alpha prime t basically. Behavior of alpha prime t. Okay? Can you see the proof of this one immediately? If it is a time, what is a regular curve? The same definition. Alpha prime t is not equal to 0 for all t. So if it is a time-like, then okay. So if it is a time-like, and it is alpha prime t, comma alpha prime t, time-like. So it is given it is less than 0. It is not equal to 0. It is not equal to 0. So for the time like it is less than 0, so it is not equal to 0. In the light like if it is 0, then curve will be 0. Then also we are done. So time like and light like curve is always regular curve. If you are only the space like curve may not be regular, and the curve may not be any of above types. For example, if you take this curve, expression looks bad. So you can you can start very simple example, asking circle and other things. I'll give you one more example. But here, for this curve, calculate alpha prime t, So basically, it is a space-like in this, and it is time-like, space-like here. Here means space-like in this direction, space-like here. And the time-like in -1 to 1. And the light-like. So curve may not be any of these type. Somewhere it is, at some places it may be space-like. Cos t, sin t, 0. Simple example, na? Alpha t equal to cos t, 0 sin t. Tell me, this curve is alpha t. Alpha t. Sorry. Yes. Two curve, alpha 1, alpha 2. Tell me, alpha 1 is space-like, time-like, light-like? Quick. So, so what is alpha? Let me do for alpha 2. Alpha 2 prime t is equal to minus sin t 0 cos t. So calculate alpha 2 prime t to check. And what is that? This is equal to sin square t minus cos square t. Sin square t minus cos. So sometime it is 0, sometime it is, so at some point t, when the cos square t is equal to sin square t, so sometimes it is regular, sometimes it is space-like. So the circle, so-called circle. Here the definition of the circle is different. Circle means the people have feeling that everywhere it is a equal curvature basically, or so that definition will not give you this expression of curve. If you start from, in Euclidean space, you have proved if you start from the constant curvature in the plane, it will be of this form, up to rigid motion. But in E13, this is not the case. If you start from a constant curvature, circle, this expression may be different. So I won't call this is a circle. I won't call this a circle. This is a map. This map and this map. This map is not, sometimes it is space-like, sometimes it is time-like. So don't think like this. Space-like means given alpha may be any of. Space-like, it is an open property. What do that mean? Space-like at T0 means there exists an interval where it is space-like. Okay? I assumed that alpha, our curve is a smooth curve. So in particular, continuous curve, use that property basically. It is a time-like, light-like is a closed property, but the space-like and time-like both are open property. If it is a point T0, if it is a space-like, this means what? Alpha prime t is greater than 0. If alpha prime, is this clear now? If it is not, if alpha prime t is not equal to 0. And then, so consider a map ft equal to t goes to alpha prime t, it is not equal to 0 at some point, so there exists, because it is a continuous map, so there exists an interval around t0 where this is not equal to 0. Okay? Yeah. There are not closed curve that time-like or light-like. This means there is no theory of a closed curve or having time-like and light-like. In this talk, in the next 1 or 2 days, we will be asking this type of question. Take a closed curve, maybe putting some condition, analytic or other things. Does there exist a minimal surface or maximal surface containing that closed curve and having normal? Anyway, so you start from a closed curve. Does there exist a maximal surface containing that curve or minimal surface containing that curve after we defining the maximal and maximal surfaces? So we won't ask for the time like. If we are starting from the closed curve, so we will say like this. Statement will be like this. Take a space like closed curve which is a space like. Or space, or just as soon as I write closed curve, so this means the space like. Otherwise, it will be null curve basically. So there are not closed curves. So what will happen? Can you prove this thing? Start from it. Suppose it is a closed curve, alpha t. Alpha t is write down alpha t equal to x1, x2, x3. It is a alpha 1 t, alpha 2, alpha 1, 2, alpha sorry, I said x1, x2, x3. So alpha t is x1 t, x2 t, x3 t. It is a closed. So this means what? There exists a point Z naught, T naught, such that x3 prime T naught is equal to 0. Clear? Smooth curve in particular. Sorry. And then, so this means what? There exists a point, so this means what? Alpha prime T naught equal to x prime T naught, y prime T naught, comma, 0. Because z prime T naught is 0. I started that point. So what is alpha prime T naught, comma, alpha prime T naught? It's x1 prime T naught square plus x2 prime T naught square. And that is greater than or equal to 0. That, do you understand? That is greater than or equal to 0. That can't be timelike. It may be lightlike. So lightlike means what? This means x1 prime t and plus x2 prime t equal to 0, t naught. This means what? If it is equal to 0. So x1 prime t naught equal to 0, and y1 prime t naught, x2 prime t naught equal to 0, and x3 prime t naught equal to 0. This means what? At t naught, x1 prime t naught and x2 prime t naught and x3 prime t naught equal to 0, 0, 0. That can't be lightlike. So go through the proof of this. Easy proof, but at least to get used to of. These are not, just get used to of all this basic stuff. Okay. So let's move to the surface in E13. Space-like and time-like surfaces E13. There are two, so I started from an immersion. So definition is written on the board, but let me explain here. So what you do, I will say x from M to E13. First of all, I will start from a map. E13. M is a two-dimensional manifold, I said somewhere. M is smooth connected surface. Yes, that's good. Surface, you know, sphere, torus. In picture, you can take an open subset of a complex, R2. That will really help. That's all I need basically. Because sometimes when I see for M, we'll see ki, what those extra conditions are required. Basically, I will come to that. But to understand, let us assume M is a open subset of a complex of R2. Open set, or just a disk. You can just have a picture basically. Okay, so clear? And then this is the immersion. So smooth connected surface with boundary. So suppose if I am taking disk here, so with a boundary, possibly boundary, because we will be needing this thing. Why did I start from the boundary non-empty? So to define this space-like time-like surface, before going into the second line and other things, let me first of all concentrate the first sentence. MB is smooth connected surface, possibly boundary is non-empty. See. What happens in the E13? What is the motivation? Just I will tell you the motivation. Technicalities we'll see later. So motivation is we have seen in the Euclidean space. If you take a torus, so why torus? You take a sphere first example. So what is the boundary of this surface? No boundary, na? Yes, there is no boundary. And this is a compact surface, closed and bounded subset of R3. This is a compact surface. Clear, na? Torus. What is the boundary of that? So there are compact surface without boundary. There are compact surface. Here we will see this type of surface are not possible. So if I start from boundary empty, so there is nothing to study. We won't left with any examples here. So we will see. This is in the plan basically. So we will see if a compact surface, and I will come to that. And if you start from any immersion, then boundary must be non-empty. So this condition is here important for to have something to study. So to understand, let us take an open subset of complex plane, open subset of R2 with boundary. This is our aim, to just have a picture, and X is a immersion. Now what you do, yeah. Okay, yes, it will be good if I, first of all, because I said for the boundary, and then what do you mean by immersion, first of all? Immersion. So, F is a map from some, because I just need some open subset of complex plane, just to this, or not just manifold. So what do you mean by immersion basically? Immersion means you calculate the derivative of, see, you have two parameter xt. You have two parameter xt. So del x over del s and del x over del t. You calculate this thing. This is basically, so these are independent at every point. These are independent at every point. That is immersion. X is any map. I'm talking about the partial derivative. I'm taking a smooth map, but may not be injective. We don't need to talk about del x by del s and del x by del t. So immersion may not be injective map. So every point you can define in some sense tangent space. In general, okay, let me tell you in general what is the definition. Suppose you start from two surface f from M to N, and this is a smooth map. Let me and then calculate the derivative of f at point P. So this will be a map. This will be a map we can discuss in tutorial. This will be how to calculate the derivative of map. So this map is an injective map basically. Then we for every point P. Then we say that F is an immersion. Yeah. So see immersion. So this is a immersion. This is an immersion. This is an immersion of circle to R2 by. Okay. So immersion may be self-intersection. This may be immersion of something. Immersion may be self-intersection. And what is the embedding of M to N? Embedding means see. This M, first of all, embedding means okay. So it is a diffeomorphism. I don't know whether I should use this word. So M is a diffeomorphism to its image via F. So this means this is asking too much. Too much in a sense that it may be their objective immersion. But that may not be embedding because we are asking the topology is also same. Topology of f of m. Yes. So immersion means here for our purpose just a map from x from u to E13 where del x over del u, del x over del s and del x over del t are independent, and these are the smooth. These are independent, and X is a smooth map. So maybe the self-intersection. Maximal surface is what you do. You just take a pullback metric. So this means what you take. You put some point P in U, and then you you define X. You define what will be the tangent space of P at U? This is a U is subset of R2 na. So this is a R2. So you take two map V and two element V and W in TP of U, and you define this is basically it goes Y. Simple way I will write very soon. Yeah. So because this is an E13, this is an E13. So you define this is a new. So I will let us denote X star. X star at P. So pullback metric. So in this pullback metric, this space, if this space becomes space-like, then we say that immersion is a space-like immersion for every point P. And if it is time-like, then time-like immersion. So this is the way basically. So let me again recall what I said. So you have U, you have even 3, you have a map X. So what you do, you fix some point P in U. So P in U, you have a TP of U just R2. So you take two vectors V and W here, and then see via that map where does those vector goes, and define V in this space TP of U, that is R2. In this space you define V comma W is basically dxPV comma dxPW in the Lorentz-Minkowski matrix. So in every point P, every point P here you are associating R2, and you are associating one metric here. And if this metric for every point P, if this matrix becomes with this metric, if this space becomes space-like, then it is a space-like immersion, and time-like immersion. If all the tangent space are space-like, it is a well-defined because X is an immersion. So if I want to check, let us have some examples here. This is a sphere. So the map is identity map basically, and then if you want to check whether this surface is a space-like immersion, so it's, S2 even 3 basically I'm asking this thing, whether I from S2 to even 3 is a space-like immersion or light-like immersion or time-like immersion. So so basically, so what you do, you just calculate. So this is a sphere. You just calculate, you fix some point P here, and you just calculate the tangent space at that point, and take two vectors V and W. V and W here. What is the and then what is the pullback metric V and W? X star V and W. That is basically that turns out to be V and W because it is a dxPV, it is going basically dxPV going to V, and then it is W. So and check whether this in this metric TP of M, whether TP of M is space-like, then it is a space. At that point, it is a space-like immersion. It is time-like, then time-like immersion. Topology of even 3. What is the topology of even 3? Topology is even 3 just a topology, vector space topology. It is vector R3 is a vector space, na? It is topology of R3 here. So it is clear, na? So space-like, time-like, and light-like. Again is the case of the again is the case of curve. We have seen surface may not be one. This is sphere. Again, this sphere is sphere in this region on these two caps. These are space-like. If you restrict S2 in these regions, this is a space-like. It is a space-like immersion here and here, and it is time-like. This in this region it is time-like, and on both circle intersect this circle and this circle intersects to this plane. This is a light-like immersion. So this is very simple calculation, but do this calculation. He will be doing. Yes, you have a question. Yeah. TP of M. Very good. V and W is in TP of M. It is isomorphic to R2 vector space, but it has two components. You're very good. Yeah. Even 3. That has 3 coordinates. Yeah, okay. Yes. So basically when I write V equal to this, then I am identifying this space. This space is basically as a subspace of even 3. and then correspond that V is in that even 3. So with this TP of M, you are thinking this is basically even 3. So but the things which I have written is not. I really appreciate your way basically. So in the beginning, you just calculate what is that. I will call bar then. You calculate that, what is that, and then see what is the relation between V bar and V. If it is map is I basically, then see what is that. Yes, this is the way basically to calculate. Fix, do this calculation, and then yes. I'm thinking like that with when I wrote this identification, but that is not a good way basically. Otherwise, I should write V bar and V W. But check it basically. What is that? DIIP. What will it give? Anyway, let's. So is this clear till now? Till now what we learn? What is the E13 space, and what is the curve? What are the curve here? Curve may be space-like, time-like, light-like. Maybe one curve may be any of 3 types. In some parts, space-like immersion, time-like immersion. What is the space-like immersion? In every curve, every tangent space are space-like. In the pullback metric. Okay. And then there are examples. No, to get used to of this definition at least. I just put one exercise here. Let's see the proof of this. To understand at least, get used to of this time-like and space-like and light-like subspaces. So suppose it is a space-like, time-like immersion, then boundary is non-empty. It is a compact. Space-like immersion means what? Every tangent space is space-like. Every tangent space is space-like, so what is the perp of that tangent space? Can you tell me? Every tangent space is space-like. What I'm saying, I'm just trying to prove for the space-like. Suppose it is a space-like immersion, then the boundary is non-empty. Okay, time-like is the same thing. So suppose it is a space-like immersion, then means what? Then means every tangent space is space-like. So TP of M is space-like. TP of M is space-like. So TP of M perp, prove it, this is time-like. In the beginning, I have written one exercise. If V is a time-like, then RV perp is a space-like. So TP of M is 2 dimensions. So do it. So this is a time-like. So we have this information with us. Somehow, as soon as you have compact, what is the basic techniques which most of the time you use basically? Compact surfaces, continuous maps attain maxima and minima. Somehow this type of things we will. So let us take A is a space-like. A is a vector in E13, space-like. Start from here. And write down a map F from M to E13. M to E13. In our case, I have just put here U basically, but M to E13. So F of P goes to via X. So XP comma A. Does this make sense? This makes sense. Because X is an immersion, X from M to E13, you have started from a space like? Yeah, tell me. No, E13, no? Oh, sorry. Yeah, that's right. Sorry. Yeah, thanks. F from M to R. This is an R. So we can just do the. What is the DFP derivative map at V? You just this is basically calculation. Do it, and this will be dxp v comma a. So Suppose, so start from X is a space like, suppose X is a space like immersion, there will be some point P naught, where df P naught is zero map. This means what? This means, assuming M is a compact basically, so there will be P naught. So this means what? dxpv comma A equal to 0 for all V, TP of M. So this means what? A lies in the perp of TP of M. So this means what? A is a timelike, but you start from A is a spacelike. This type of techniques. Using the compact set and interior point you have a P naught, then it will attain a minima. So take a P naught, so that will be critical point. So df P naught is equal to 0. So the proof and everything is given in the Rafael Lopez, this text. So don't get panic, you just copy, try to get used, try to get assimilate, and then you can see the proof there. Or discuss with me outside the. Everything is here, everything is here. Everything, nothing else. Just. So, because there is a critical point. There is a critical boundary is empty, it may attain maximum in at the boundary, so then you may not have a derivative 0. So using the yeah. Compact, boundary is non-empty. Yeah. Some examples. Hyperboloid of center P naught. Yeah. Just see the definition, just see the expression which I have written. Expression is P minus P naught. P minus P naught minus R square, and what is the last thing basically? Last thing is P minus P naught E3 is less than 0. E3 is E3 by E3 I mean 0, 0, 1 vector. So what does this thing says? This thing says I'm taking basically one component. I'm taking one component. My definition of a maximal and minimal surface, maximal surface are the connected surface basically. So just to take care of these things. So this is this surface is a space-like surface. You calculate the tangent space at every point. Induced matrix, check it. Positive definite it will be. It is a space-like surface. It is called the hyperboloid. These two things are not space-like. By definition, I am taking one of these basically. By definition, I am taking connected set. X square plus y square minus z square. This is minus z square. Okay? So put P naught is 0, and then so it is minus z square. This is called the de Sitter space. De Sitter space. This is timelike. Everywhere it is timelike. Astronomer, de Sitter was astronomer. So de Sitter space he has. So again, these things you basically will be you can at least one of. So we have 3 examples. One is this, and this, and this one. So this one, 1, 2, 3. Proper calculation at least. Proper calculation. You do at least one of these. Okay. Yeah. One more important fact is now let's just concentrate ourselves in space-like surfaces. Because minimal surfaces are space-like, maximal surfaces which we are going to define are space-like immersion. Main curvature vanishes in the first slide I have written basically. Space-like. So just consider it space-like surface. So one more property of a space-like surface, interesting property, is that these are orientable. There are surfaces in even in Euclidean space. Those may not be oriented, grand-modal, or you have seen. So there are surfaces. Here the space-like immersion, it is an orientable. So there is no theory of this type, non-orientable maximal surface. No, don't go there. We don't have any basically. Maximal space-like immersion is orientable. So proof is really very easy if you understand basic techniques. What is the space-like immersion? What is the orientable first of all? You can define a normal at every point, neighbor 0. So what is the normal here? Normal or timelike? What are the normals? If you have a space like, this means tangent space are space-like. So what is the purpose of that? Timelike. Timelike are never zero. So you just fix a convention key, which one you will take, because you are in connected component. You are dealing with the connected surface. So fix which, because normal is never zero. So it may, if you take the unit thing, so it two basically. One is, if one is n, other is minus n. You have two choices. Which one you will so fix one basically, because you are connected surface. So that will give that makes it is an orientable. Picture is clear very much now. It is a space-like, so normal is time-like. Normal is never zero, so you have to fix one. So this is the yes. So now we have we have at least a basic understanding of Lorentz-Minkowski space. Time is 12:30. So now we are basically in situation to define, to go to the first slide basically, and define. This was the first slide. Now, okay, we do not know what is the mean curvature here, so let's give you the meaning of the mean curvature basically for the space-like surfaces. Space-like surfaces are what? Space-like surfaces are where that metric is positive definite. So that works as a Euclidean metric in every tangent space. So what you do, you have a space-like surface, you define the normal. Normal is xu cross xv divided by, that is, see, there are few points. What is if you have a vector, if you have a b vector, what do you mean by a cross b? It's to define the normal in the Euclid, in this space. So a cross b are that vectors which, if you a cross b is basically, if you define is a cross b comma x metric basically. So it will be determinant of a comma b comma x. If you define a cross b like this. So that is a unique, that turns out to be unique vector, and that will say J cross B. It doesn't, definition may not match with the Euclidean space definition. Definition matches, but the expression calculating way may not matches basically. May not need, it doesn't match. So basically what is A cross B here is, you have A and B in R3, you calculate A and B in even 3, you take think A and B in R3, you take the cross product there, take the reflection along z equal to 0 plane of that vector. And that will match with our A cross B here. This is just a result I am just mentioning here, to have a feeling how to calculate the A cross B. So in the Euclidean space, if you have A equal to A2 j plus A3k, in that notation basically we learn A cross B, and the B equal to B1I, B2j, B3k. So A cross B is you put ijk, and then A1, A2, A3, you calculate that. So here what you do, you put minus k there. Ij minus k, A1, A2, A3, B1, B2, B3, calculate that. That will be A cross B here. In that way, basically. So what I'm saying, you have a meaning of normal here, still. You have a meaning of normal. What is the mod n here? These are the basic things you can see. Mod n you can't define because VV, in the Euclidean space, that is equal to inner product of VV and the square root of that. Here VV may be 0. So what do you take? You take the modulus inside. Just a little bit, basically, way to get out of that. So, what is the what is the modulus of some vector? Is basically square root of inner product of square root of modulus of trick VP. This you calculate. So, by this way, you have a normal, you have a Gauss map here. You calculate the derivative of that. And then you will see this space in this metric. That in this metric, because these are space-like. Again, that is a self-adjoint. And then you have again eigenvalue k1 and k2. You have an eigenvalue. That is diagonalizable. The same thing. Point to mention here, this way will not work for the time-like surface. If you take the time-like surface, if you start from a time-like surface, in place of space, time-like surface means time-like immersion. In place of space-like immersion, that metric, that DNP is self-adjoint, but that may not be diagonalizable. So you can't define the principal curvature for the time-like and light-like, time-like immersions and other things. But for the space, but still there is a way to go out of that. Go into that. So, but here here this metric is basically the same calculation will work because it is diagonal. You have k1, k2, define the k1 plus k2 by 2, and then that is a mean curvature, the similar way. And the mean curvature vanishes, then we will say that is a maximal surface. And the meaning of maximal is basically, it turns out to be a local area maximizing in that metric, this type of immersions. Go through the definition only. We understand every word here. Maximal surface in 3-dimensional. Okay, so there may be some other dimension. Lorentz-Minkowski will not go. Here, 3-dimension. Lorentz-Minkowski is a space-like immersion. Every tangent space is a space-like. Of 2-dimensional manifold M, don't worry about 2-dimensional manifold M. Just a sphere, torus, this type of things. Or just or more, if you want to understand first as a first time, if you're looking. So just open subset of a complex. It's mean curvature vanishes. So to understand these type of surfaces, let's again we'll see we will be using M equal to OU, open simply connected open set. And then do the same calculation basically. Oh, calculation I erased there. So similar to the minimal surface case, if M equal to U, be simply connected open. Simply connected, do you remember why I'm taking? Because that integral makes sense basically at the and then you have x equal to x1, x2, x3. We define similar because these are the operator. You define del by del z xk by this way, and then because of the mean curvature things, you will see that this is equal to 0, this is greater than 0. And again, the first condition is because of isothermality. I did not write isothermality. So if x is an isothermal, the first condition is isothermality, if it is an isothermal parameter and the second condition is, in this metric, it is irregular. In this metric. See here, just see the change, minus phi 3 square, minus mod phi 3 square. Metric is different here. In this metric, it will turn out to be greater than 0. And phi is a holomorphic. If so, only ultimately result does method is changed to write down all those things. Not that much, but here you have minus, and then now you have feeling at least. If first condition is for the isothermality. Second condition, when I say first, this means phi 1 square without modulus. Okay, and now maximal, it is minus phi 3. Minimal, it is plus phi 3. And then when I say second means the regularity, minus modulus. And the simply connected I am taking because of the integral makes sense. This is the again, either you do for the minimal surface case, either you do for the maximal. Do at least once to prove that if you start from a minimal maximal immersion, how did you get xz, and then prove that del x by del z, del xk over del s minus del I del xk over del t is basically phi k. Do this thing at least to see. Again, it's the same way. You start from a phi 1, phi 2, phi 3. You get if we satisfy these conditions, it is a maximal immersion. Both way. If you start from a maximal immersion, you will have even phi 1, phi 2, phi 3. If you start from a phi 1, phi 2, phi 3, holomorphic form. Form means don't confuse with form. This is just a way of writing. Here, phi 1 equal to some function dz. So here I did not write integral gamma z phi 1, phi 2, phi 3 dz. So basically that is hidden here when I say form, one form. If you don't know the form, another thing. So phi 1 is, suppose phi 1 equal to z dz, like that basically. Phi 1 form dz is there, and then this is a maximal immersion. Remember again, immersion may not be injective. So if you graph those pictures, those may be those may intersect. As we did for the minimal surface case, if you relax the last condition, second condition, then also it is not identically equal. So these two lines, the equal in cut, this means identically equal, not identically equal to 0. I mean to say this thing basically. The second condition, this condition, I mean not identically equal to 0. Not equal to 0 means not identically equal to 0. So this is a maximal, generalized. Generalized means, you know what I'm allowing? I'm allowing that the surface may not be regular at some point because of the second condition. And the simply connected I started because I want integral makes sense, because I know how to define the maximal surface in terms of integral. Suppose if I remove the simply connected, then the third condition I have to add here. Integral makes sense basically. High real periods of integral that vanishes. Means integral makes sense. I have to add that condition. So either you put the simply connected or put that condition. But take care of all those things. When you read the text, why these conditions are there? Why this? Is this clear? And the XU is said to be generalized maximal surface. Immersion is said to be generalized maximal surface. Put phi1 equal to, take the random phi1, phi2, phi3. M equal to C. Phi1 equal to this, phi2 equal to this, phi3 equal to Z. Then calculate, see, phi1 square plus phi2 square minus phi3 square will be 0. Mod of phi1 square plus mod of phi2 square minus phi3 square will, mod of minus phi3 square will not be identically equal to 0. And this will, and then in the parameter, this is the maximal inner surface. Phi1, phi2, phi3. Now you have a lot of examples, no? You have a lot of examples. Phi1, phi2, phi3. Maximal helicoid. It is, name is coming from the minimal surface case because there is a relation between the inner surface and the maximal inner surface, maximal helicoid surface and the helicoid surface. There is a relation. We'll come to that in the next talks, basically. So you have there are a lot of examples. So in the next talks, I am planning to. What is the purpose basically in these remaining two classes? Basically, what are the method to get the new maximal surfaces? So one is basically this is the method. See, we are getting now maximal surface by just what starts in upper representation, Bjorling representation. Then can we have some other method basically, which we have done in the last research problem. So we will see what is the method basically. People are interested to have new maximal surfaces, minimal surfaces. So the talk will go like this. Just a quick overview to have an idea. Different approach to understand the maximal surface. Basically, can we have some other maximal surface? One more maximal surfaces from this approach. And then given a strip, can you find a maximal surface? Given a curve, can we find a maximal or minimal surface? So Bjorling problem is basically, so given a plane, can you find a minimal surface which intersect that plane orthogonally? Like that basically. So this is a minimal surface. So this talks to go and basically this way. So I will stop here.